motors, lights, tools, communications equipment, circuit breakers, and so on. They all depend on alternating current, and they all depend on you to keep them in good working order. Alternating current is what we're going to be talking about in this unit. What it is, how it works, what factors affect the operation of the AC equipment in your plant. In this first segment, we'll be laying some groundwork. We'll review the way that alternating current is produced. We'll look at a couple of waves, and we'll define some of the terms that we'll be using later. In other segments, we'll cover inductance and capacitance, and then we'll put everything together in a discussion of AC power and the development of single-phase and three-phase systems. As you know, there are two types of current: direct current, which we usually call DC, and alternating current, that's AC. Here's a simple DC circuit. The power source is a battery, and the load is a resistor. Direct current always flows in one direction. Here's a simple AC circuit, which contains an AC power source and a resistor. Alternating current flows in one direction, stops, and then flows in the opposite direction. AC changes direction so fast and so often, many times a second, that we can't detect the change. However, the fact that AC changes direction periodically as it flows through a circuit is very important to anyone who works on AC equipment. You'll see what I mean as we go along. Well now, there has to be a reason why AC changes direction and DC doesn't. So let's take a closer look at the two types of current flow. As you probably know, current always flows from the negative terminal of a power source through a circuit to the positive terminal of the power source. That's true for both types of current, AC and DC. The difference is in the operation of the power source. This circuit has a DC power source, a battery. The battery has a negative terminal and a positive terminal. Current flows from the negative terminal of the battery through the circuit, through this resistor, and back to the positive terminal of the battery. In this DC circuit, and in all other DC circuits, current always flows in one direction. The negative terminal of a DC power source, like this battery, is always the negative terminal, and the positive terminal is always the positive terminal. A shorter way to say that is to say that a DC power source has fixed polarity. The current it produces always flows in the same direction. Power sources for alternating current are different. They don't have a fixed polarity. The polarity of an AC power source changes periodically. As the polarity of the power source changes, the direction of current flow changes too. We can get the whys and how from this simplified AC generator. This generator is going to be our AC power source. We'll see how it produces a voltage that causes current to flow through this circuit, and we'll see that current light up this light bulb. The generator produces voltage by means of induction, a process that you may already be familiar with. To review briefly, a voltage will be induced when three things are present: a conductor, a magnetic field, and relative motion. In this simplified generator, this loop of wire is the conductor, and the magnetic field is provided by this magnet. The relative motion comes when the conductor is rotated between the poles of the magnet. There are two more important components in this generator: the slip rings and the brushes. The slip rings are on the ends of the conductor. They slide against the brushes as the conductor rotates. The current produced by the generated voltage flows through the brushes and then on through the circuit. If we look at the conductor head on rather than from the side, we can see what happens as the conductor moves through its rotation. We'll take out the slip rings and the brushes in this view, so it will be easier to concentrate on the conductor. We'll put the slip rings and brushes back in a few minutes. Now, as the conductor rotates, it cuts through the magnetic field between the two poles of the magnet. As you can see from this angle, the magnetic field is made up of a number of lines of flux. Each half of the loop of wire cuts through these lines of flux in two different directions, down and up. Because the conductor moves in a circular pattern, we can think of it as starting at 0 degrees and rotating through the full 360 degrees that make up a complete circle. From here, 0 degrees, to here, 180 degrees, this half of the conductor is cutting downward across the lines of flux, while this half of the conductor is cutting upward. From here, 180 degrees, back to here, 0 degrees, the situation is reversed. The half of the conductor that was cutting downward across the lines of flux is now moving upward, and the half that was moving upward is now cutting downward. I said earlier that the polarity of an AC power source changes. Well, the change takes place here, when the direction in which each half of the conductor cuts across the lines of flux changes. When this half of the conductor is cutting downward across the lines of flux, it has a positive polarity. The other half of the conductor is cutting upward across the lines of flux at that time, so it has a negative polarity. The direction that a conductor cuts a magnetic field, or the direction that a magnetic field cuts a conductor, determines the polarity of the voltage that's induced. A good way to see this relationship is on a graph. This graph has a vertical line and a horizontal line that starts from the middle of the vertical line. We're going to use this graph in just a minute to plot the voltage that's generated when the conductor in our simplified AC generator rotates. To prepare you for that, let me point out a few things about the graph. The vertical line represents the magnitude of the voltage. If the voltage is above the horizontal line, it's positive. Voltage that's below the horizontal line is negative. The horizontal line represents time. One more thing. If the voltage is on the horizontal line, it's neither positive nor negative. It's 0. Now, let's rotate the conductor and plot the AC voltage as it's generated. At the beginning of the rotation, the AC voltage graph shows us that the induced voltage is 0. The conductor hasn't started to move, so no voltage has been produced. When the conductor starts to rotate, the line on the graph shows us that voltage is increasing. The voltage reaches its maximum positive value when the conductor is at the 90-degree point, 1/4 of the way through its rotation. That's the point where the conductor is cutting through the maximum number of flux lines. It's moving through them at right angles. Voltage then begins to decrease, and it continues to decrease until it reaches 0. At this point, the conductor is halfway through its rotation at 180 degrees. It's cutting through no flux lines because it's moving parallel to them, so the voltage is 0. As the conductor moves from 180 degrees to 270 degrees in its rotation, it cuts through the flux lines in the opposite direction, and voltage starts to increase in the negative direction. The voltage reaches its maximum negative value when the conductor is at the 270-degree point, 3/4 of the way through its rotation. The voltage then decreases until at 360 degrees it's back to 0. Here, the movement of the conductor is parallel with the flux lines, just as it was at the beginning of the cycle and at the 180-degree point. This kind of curve that we've been plotting is called a sinusoidal curve, a sine curve, or a sine wave. It has no sharp bends or straight portions, just a smooth rise and fall. We'll be seeing a lot more curves like this during the course of this unit. In fact, we're going to look at another sine wave right now. The voltage that we just saw being generated causes current to flow when there's a complete circuit to provide a path for it. Now, let's go back to the first view we looked at. The slip rings and the brushes are attached. We have a complete circuit with a light bulb to act as a load. As the conductor in our generator rotates, we're going to plot both voltage and current. As the conductor turns, both voltage and current build up to a maximum positive value and then decrease to 0. At this point, both voltage and current reverse direction and build up to a maximum negative value. Then they decrease to 0 again, and the cycle is complete. In this case, what we mean by a cycle is one full rotation of the conductor through 360 degrees. A cycle is also one complete sine wave from the starting point through the positive part of the curve, then the negative part, and finally back to the starting point. During each cycle, the current flowing through the light bulb causes it to brighten, dim, go out, brighten, dim, and go out again. In a typical AC power system, this cycle is repeated 60 times each second. It's so fast that the bulb looks like it's on all the time, even though it's actually turned on and off periodically. Before we leave sine waves, let's look at them more closely and define a few terms. The amount of voltage or current at the maximum positive or negative point is called the peak value of the voltage or current. The peak value occurs twice in each cycle. There's one positive peak and one negative peak. The amount of voltage or current between the positive peak and the negative peak is called the peak-to-peak value. Now, even though it may be handy to know about peak values and peak-to-peak values, these values aren't commonly used. Most of the time when we're dealing with AC, we talk about effective values. The reason for using effective values rather than peak values with AC is that alternating current doesn't maintain a constant value. It doesn't build up to a peak and stay there like direct current does. For example, a 100-watt light bulb won't put out as much light in a circuit with 120 volts peak AC voltage as it will in a circuit with 120 volts DC. As we just saw in our circuit with the simple AC generator, the bulb with AC is off part of the time. Because of this, the total amount of light is less than it would be with DC. With DC, the bulb would always be on. To find the exact relationship between AC values and DC values, scientists did a lot of experiments to measure the heating effects of AC and DC power. These experiments proved that AC power and DC power are not equivalent. Since power is equal to current times voltage, the scientists were able to express their findings in the following terms. 1 ampere peak value of alternating current produces the same heating effect as 0.707 amperes of direct current. This same relationship applies to voltage because voltage produces current. This effective value for AC is often called the RMS value. The letters stand for a mathematical term, root mean square. The mathematical formula doesn't concern us here. What's important is that when we refer to values of AC current and voltage, we usually mean the effective values, that is, the RMS values. RMS values are used to rate AC operating voltages on everything from industrial equipment to power lines. Most meters read RMS values. You can take it for granted that the rating of an AC motor is the RMS rating, or that an AC meter is reading RMS values, unless the data plate on the motor or meter says otherwise. Okay, now that we're clear on what is meant by RMS values, peak-to-peak values, sine waves, and cycles, let me give you one more definition to remember. Frequency. Frequency has to do with the rate at which AC cycles are completed. It's the number of cycles completed each second by a given AC voltage. Frequency is usually expressed in hertz. 1 hertz is 1 complete cycle every second. If 60 cycles are completed every second, the frequency is 60 hertz. Well, that's enough definitions for a while. Read through section 1 in your text and make sure you understand what we've gone over so far. If you have any questions, ask your instructor about them.